Hello, everyone. My name is Kelly Hall. I'm a marketing coordinator for ALS North America. I want to thank you all for joining us today for our Webinar Wednesday series. Our presenter today is Dwayne Bennett. Dwayne received his Bachelor of Science in Chemistry from St. Xavier University in 2005. He is a professional chemist as a member of the ACPA, as well as the current president of the ACPS. Dwayne has been with ALS for 10 years and is an expert in particle size analysis. Now he serves as the technical specialist at our ALS laboratory in Saskatoon. Today, Dwayne will be discussing particle size analysis. During this presentation, feel free to use your chat box, ask a question, or raise your hand features to ask questions. All of these questions will be answered at the end of the presentation. Dwayne, thank you for taking your time to deliver this presentation today. I will go ahead and turn it over to you.
Thank you, Kelly. So as Kelly said, I'm here to speak about particle size analysis. And today we're going to be focusing more on the analytical side of things, as well as the application of the particle size analysis. So to start today off, we're going to start off with the safety moment, which is just how ALS likes to start all their presentations, followed by an introduction to particle size. What does particle size mean, and how do we go about it? Followed then by methodology for particle size analysis, because like a lot of different methods, there's different ways of doing things based off of the particle sizes and the particles in question. And then finally, we'll go into some of the applications of particle size analysis results. So for our safety moment, I like to choose driver safety. Here in Canada, especially in the prairies, we start to have a little bit of nasty weather that's come up, and so it's very important to approach driving in a safe and conscientious way. First thing is always make sure not to drive under the influence of drugs and alcohol, and that includes any prescription drugs. Always wear a seatbelt while driving, and make sure your passengers are wearing their seatbelts. Never use handheld mobile devices while driving. And if you're making a long trip, consider fatigue management when you're making that trip or planning that trip. That might mean taking regular breaks or having a second driver available to switch off after length of time. So moving into particle size analysis. Particle size analysis and particle size is a physical property of the soil, which is directly related to how the soil will handle mobility of water or hydraulic conductivity, as well as soil vapor mobility. So these are tools that are very important for identifying remediation guidelines, and if there's a contamination source, how quickly or how much of that contamination will spread to adjacent areas or potentially into the watershed. It is also a very important property for construction, engineering, and roadway projects, where this particle size of the soil can affect how high a building could go, how stable a bridge would be, or how good a roadway will hold up to environmental factors. So when we're talking about remediation considerations, in Canada we have the CCME guidelines, which are based off of 0.075 mm. If you have particles that are mostly greater than that, so greater than 50%, then it's coarse material, while if it's mostly less than that, it will be a fine material that can change how you look at the soil and how you look at contamination risk. And the regulatory requirements will change based off of this fine coarse classification. It can also, particle size can also be used for fill soil evaluation or general soil property consideration. When considering soil nutrients or looking at fertilizer recommendations, the particle size can be used to help estimate what type of uptake you need or what type of fertilizers you need. And these types of evaluations are typically based on clay, silt, sand percentages to classify the soil type. In Canada and the US, we have different ways of evaluating it, but both of us use soil triangles to evaluate. The Canadian system uses percent sand and percent clay with a nice right angled triangle, where if both the percent sand and clay are 0, it's 100% silt, while the US soil triangle is based off of a different triangle where we have silt, clay, and sand. Both of them are just different ways of interpreting the same type of results. And if you have a clay 40% and a sand 60%, you would fall into the sandy clay to the clay loam type of place on these triangles. So in order to analyze particle size analysis, we do have to use a variety of different types of methods. And this is simply because no one method can handle an entire suite of particle sizes. So the methods typically start off with a dry sieve method. And this is using a stack of different types of sieves, shaking them so that the material falls through to the sieve, which has openings that will retain that, and then measuring it gravimetrically. Wet sieving is used for finer particles where a simple agitation or shaking of the sieves will not cause the particles to separate and fall through the holes. So we will use water or another solution to help wash through the material through to the next sieve. And then for the finest particles, we use sedimentation methods, which are based off of Stokes' law. So most of our methods, especially when it comes to the hydrometer method, are based off of ASTM methods. So the standard that has been used over the years since 1963 has been ASTM D422. And a lot of regulators and a lot of different standards have been based off of the D422. It has been shown that D422, while it was a standard that was well renowned and well documented, it was missing some important details and it wasn't able to be revised in such a way to make sure that all the details required for these methods could be included in it. So it was withdrawn in 2017 and replaced with two other methods. The first method, ASTM D7928, is a more specific method for using hydrometer for the sedimentation determinations, while ASTM D6913 is a replacement for the sieve analysis. So while D422 included both methods, now it's been split into two methods that allow us to have further details and further breakdowns specific to those methods. So when we go to analyze any type of particle size analysis, there is a flow chart which we use in order to determine the types of analysis that we are going to do and the order of what we're going to be doing. So with any type of analysis, the first thing that we have to look at is sample preparation, because if soil comes in, it could be a very dry soil or it could be after a rain, so there's a high moisture in the soil, and that can affect how well the samples will react while we're doing any type of sieving or any type of other analysis like sedimentation. So for sample preparation, there's a couple of different ways of going about it based on the sample type, and we have to change things up depending on those sample types. So the first thing that we have to look at is if the sample needs to be dried or if it can be analyzed as an unmodified sample. This comes down to the fact that certain samples, if you dry them and remove that moisture, it can harden or it can conglomerate into harder particle aggregates that cannot easily be broken apart. And this has been shown that drying at very high temperatures, anything over 100 degrees C, may cause physiochemical changes to occur. And my example for this would be if you go out into a field of clay and you pick up the clay, it's easily manipulable. You can easily break it down just with your hands. If you take that clay and you shape it into a ball and put it into a kiln or a oven and dry it out, it comes out and it's going to be brittle, but it's going to be very hard and come out into large chunks. The next step after drying or analyzing as received would be disaggregation. So disaggregation is a term that we use for breaking down of aggregates or small particles that come together to form clumps of those particles that could be passed as a larger particle size. The segregation is performed through the use of a mortar and pestle, and we use a rubber tip pestle in order to prevent any damage to the samples. And this can only be done if the samples will not disintegrate during the actual process. So if there's any risk of a sample being broken down, any of the larger particles are frail and easily disintegrated, then we cannot do that type of prep work. The next step to doing any type of analysis is to look at the samples and decide what type of specimen size to use. So the specimen size is based off of analytical uncertainty, which is dependent on the largest particle size in your sample. So the way that we decide this is by looking at a sample, looking at the largest particles. If you have any cobbles or pebbles in the sample, it can severely influence our type of analysis, requiring much higher samples to be sieved. And we evaluate whether or not we need more sample. For most soils, which are samples that pass through the 4.75 millimeter maximum particle size or the 2 millimeter particle size, we can typically get away with 50 to 100 grams, depending on the method. There are two different methods for doing the sieving. The method A is the referee method. We call that composite sieve, while method B is a single set sieve, which gives higher analytical uncertainty requirements, which gives us lower LORs potentially, but it is specific to certain sample types and it's specific to only doing the sieve analysis, the dry sieve analysis, and cannot then be further combined with other methods easily. So once we have the samples into a state that can be analyzed, next step would be to do a dry sieve test. So this and sieve analysis, as I said, there's two different methods. One is dry sieving with mechanical agitation, or just hand shaking them, while wet sieving is using water. The two different approaches to the sieves, the composite sieving and the single set sieving. When we talk about the referee method, which is composite sieving, the sample is separated into two portions: a fine portion, anything that passes a 2 mm sieve, and a coarse portion. And then we use those two different portions to get the subsets of the sieves, and then mathematically combine the data from each set. The reason that this is the standard is because it allows for more mechanical agitation of the coarse materials and the fine materials, and further testing on those than is typically done if you have a single sieve set, which is just using a single set of sieves, a stack. You put your sample in the top and you measure each layer. So just to give a visual interpretation of sieving. So this is a sieve stack where you have your large particles that are being retained on the large sieve, which won't pass through the holes, and then every stack lower will have smaller holes which will retain the bigger particles and let the smaller particles fall through. And this is a very good way of determining the fractions of the larger particle sizes. In order to do wet sieving or any sedimentation method, we do have to do a pre-treatment. While dry sieving is very handy for doing large particle sizes, which can be just agitated and shaken through, in order to do wet sieving or sedimentation methods, we have to do a couple things to make sure that the samples will behave as we expect them to. The first thing that we have to do, and this is dependent on the soil that we are working with, is look at the sample and decide if there's any type of pre-treatment that we need to perform. Different interferences such as organic matter, carbonates, or soil salinity can affect the analysis of the sedimentation and cause issues when we're doing any type of wet sieving of the small particle sizes. So the first thing that we do is look to remove organic matter, and we do that through a digestion of hydrogen peroxide. For carbonates, if there's a high carbonate concentration in the samples. Usually the soil looks white from the carbonate. We'll use an acid pretreatment to remove those carbonates. And for salinity, if the samples are forming any type of concentration gradient, when we go and add in our dispersion fluid, we can use washing to remove any of those salts. So we fill up this column with water, put the soil in, let the soil settle out, and then we remove the water and just do a couple washes. Once any of this pre-treatment is performed, we then have to do a dispersion technique. And the first thing that we do is a chemical dispersion. So what chemical dispersion is, and we can use one of two different chemicals typically for this, is we put it into a solution, and that solution will get in between the particles and allow them to break down. The chemicals that we tend to use are water, which it can easily get between particles and break it down, or sodium hexametaphosphate, colloquially known as Calgon solution, which is a more effective solution or chemical for doing this dispersion because it increases the polarity as the chemical gets in between, causing the individual particles to separate more readily. Once the samples have been inundated with this chemical, either water or sodium hexametaphosphate, we then use a mechanical dispersion technique in order to further assist with the dispersion of the chemicals or of the particles. So a mechanical dispersion, the referee method, ASTM 422, or the ASTM 6913, include a number of different options. The first option is milkshake mixer method, where the sample gets mixed up with water with the sample and air using a milkshake mixer, so that this will disperse it using a cup. An air device is a similar style device, except for instead of using a mechanical blade mixer, it'll jet air into the sample, causing it to froth up and mix to separate the particles. And the last method is a mechanical shaker method, where samples are shaken on a shake table. Over time, the action of the shaking will cause the samples to separate and the particles to separate to disperse properly. Using an air jet device or a milkshake mixer is the typical method because it is fairly quickly. You only have to use about a 3-minute mix using either of these in order to disperse your particles. But using either of these, they have baffles, they have blades in them, and they can cause individual particles to break down. Mechanical shaker, it's a much longer method, typically overnight, but it's a much gentler method and can prevent those individual particles from being damaged or disintegrated. Continuing on, once the samples have been properly dispersed, we are going to move on to wet sieving and sedimentation. So with wet sieving, it's typically used for finer particle sieving, where water is washed across the sample, allowing for the aggregates to break down if they've formed after the dispersion. And it also helps make sure that any of the particles that are of the small particle sizes will pass through the sieve just by coaxing it through with a solution. Moving on to the next part, which is going to be sedimentation. Sedimentation refers to the settling rate of the particles in a dispersant. This is a method that's based off of Stokes' law, which states that larger particles settle faster than smaller particles. So there are a couple of assumptions that we have to make. The first one is applying Stokes' law. All the particles are spherical particles with smooth surfaces and no interparticle interactions. So what that means is that each particle is an island in unto itself, and they're not going to interact together while they're settling. Spherical particles means that they have a standardized settling rate, and smooth particles means that there's not going to be any friction that will help prevent it from settling faster. So this is just an example of a settling technique on the side where the particles, larger particles, settle out first, then the medium-sized particles, and at the end of this sedimentation, only the fine particles are remaining in the solution. So by combining settling principles and measurements, we can determine the particle size for any reading at time t. And the particle size is determined both by two different calculations. The first one being the amount of particles still in suspension, and the second one is the size of the largest particles in suspension. The amount of the particles still in suspension, there's two different techniques for establishing that. And the first one is hydrometer. The more particles in the solution, the more dense the solution. So the hydrometer will sit higher in the solution. We can measure that. The second method is a pipette method where we actually remove a subsample of the suspension and measure it gravimetrically after drying. The hydrometer method is the typical referee method for a number of different regulators and a number of different labs. It is, as the referee method, is a method that a lot of people need to apply, and most of our labs offer this. The density of the solution is measured using the hydrometer, and then we use calculations to refer back to the actual concentration or the percentage of the material in the solution. We also, by taking the time, we can then determine what the actual settling rate is of the solution and the particles in there, and know how many of the particles or the maximum size of the particle that's still in the solution. We typically take our readings intermittently for up to 24 hours. We can extend that to a 48-hour reading as well if colloidal materials are also important. So just to give an example of some hydrometers and the relative states. So this is samples that have sat out for quite a while, so we've had a lot of settling occur. Just by the color of the solutions, we can see that there are still particles suspended in the samples. And the sample on the far left, number 43, you can see that the hydrometer is much higher in the solution. The top of it is very high compared to the other three. This indicates that the material in that, if they were all settling at the same rate, there's still a lot of material in that solution, meaning that there's a lot of finer particles in that solution. The pipette method is a slightly different take on a sedimentation method, and the reason that is offered and typically used is because, or can be used, is because it offers a lot of advantages over the hydrometer method. First off, it's a direct measurement of what's still suspended. When we're looking at hydrometer, any type of interferences, such as the change of the density of the solution from dissolved components, can affect the hydrometer as well as the settling rate. Pipette method, when you take a measurement, you're taking part of that sample, drying it, and measuring it directly. It also leads itself to a number of other advantages which can help with the testing, such as miniaturization. Miniaturization being a way that we can do more samples in a smaller space using less sample. When most people consider hydrometer pipette method, you have to consider what type of analysis comparison can be done. So we've done a number of studies out of our Saskatoon lab looking at hydrometer versus pipette methods, and I found that both methods do give comparable results. So the big thing looking at this graph, we have a pipette method as well as a hydrometer method. Everything greater than 0.1 millimeters is done by sieving, so both of those methods should be comparable because everything is done by sieve. But looking at the less than 0.1 millimeter, you can see that there's a lot, it's very, very similar results coming from both types of testing. The allowance of the pipette method versus the hydrometer method really comes down to what the regulator is allowing and what the standards are expecting. While hydrometer is a referee method, a lot of regulators do accept other methods such as the pipette method as an alternative based off of the lab. So once we've got all the data, we've got the sieve data, we've got the hydrometer pipette data, we then need to report it to the clients, to people, and have it in such a way that it's going to be usable. So there's a couple different ways that we report. For simple sieve analysis, such as a CCMA particle size analysis, we just report those specific sieves and the amount that is passing those sieves. So amount less than or the amount retained on the sieves, which would be percent retained. Then based off of that data, we can provide details and classifications based off of those results and based off of the guidance documents. So when we talk about CCME PSA, we're talking about fine coarse based around the 0.075 mm. There are other systems that we can also classify it. We also can look at the particle size based off of defined particle size ranges. So in that situation, the sand, silt, clay, as well as some other systems that we'll be getting into shortly. When we're approaching any type of particle size analysis and trying to classify the particle size analysis, there are a number of different systems that can be used. And each system has its own purposes and its own applications depending on the client's needs. Some common systems that are applied are the Wentworth system, which was developed back in 1922, the AASHTO system, which are used for roadways and highways, the International System, the Unified System, USDA system, and the CSSC system, which is the Canadian Soil Classification System. When we're looking at these different systems, there are a number of different ways of breaking it down, and typically I'd like to use a table just to show how different particle size systems work. And just looking at this system, you can see that for a number of these different systems, the clay silt definition can change, while the USDA and the international system use 0.002 millimeters. The Wentworth system uses 0.004, and the AASHTO system uses 0.005. So knowing the system defines which particle size classification system and which ranges that we're going to be looking at. In the same way that the system separating silt from sand, 0.074 millimeters is used for a number of systems, but 0.05 can be used. The CSSC system, which isn't really listed on this table, uses its own system, which is based off 0.005 millimeters, 0.05 millimeters, and 2 mm for the sand and greater than sand breakdown. Again, coming back and looking at the soil classification systems used for different agricultural purposes, we do have these two soil triangles that can be applied. Applying these soil classification systems, one of the easiest ways to review the data or look at the data is a grain size curve. And a grain size curve is based off of a percent passing criteria where you have your y-axis being the percent finer than. So as materials, if everything passes through a sieve or passes through or nothing's retained, then it's 100% passing. And then as you go to smaller particle size, more get retained, so you get an S curve. It can be used to identify soil types and mixtures, and can also be used to extract any particle size ranges depending on the classification system. So even if a classification system doesn't have a point on this curve, we can use the curve itself to generate the points in between. So how do you pick what type of particle size determination you need? So method selection is key and is based off of the regulator that is being used. So when we're looking at the sieve analysis is typically standardized across the different methods. So if you need to use a specific sieve stack, it doesn't matter if the regulator wants a pipette method, a hydrometer method, or a different type of method. The sieves are standardized and they're typically going to be based off of the meshes, which are controlled through ASTM or Tyler meshes. The choice between sedimentation methods can be prescriptive, so we need to know what you're looking for. And if we're looking for CCME fine coarse classification or PSA classification, it's fairly standardized. But when you go down to a grain size curve or D50, directed 50 for our Alberta clients, they might have a little bit more specific ways of approaching that. So the most simplest type of analysis of the particle size would be a fine coarse classification. And this is used both in CCME and Alberta Tier 1 applications. And we break it down into fine materials, coarse materials, or very coarse materials based off the 0.075 millimeter and the 2 mm portions. Fine and coarse materials are split between that 0.075 threshold, while very coarse materials are based off a 2 mm. And these particle size thresholds can affect what type of application that area or what type of guidance we can use for those areas. So just to get an example with CCME, fine coarse grain materials and looking at hydrocarbons in the F3 or fraction 3 range, diesel and motor oil range. If it's a coarse grain material, because of higher mobility, the actual regulations are much lower at 300 milligram per kilogram for that type of soil, compared to fine grain soils where that mobility is reduced, which has a much higher regulatory limit for 1300 milligram per kilogram. If the material is very coarse or greater than 90% 2 mm, it will require special attention. In a situation with Alberta, instead of being a tier 1 approach, it should be a tier 2 approach. When applying nutrient testing, we look at a different type of classification system based off those two soil triangles from earlier. And the soil triangles will give us a texture class of the samples, which can affect how we're going to apply certain density applications to that particle size and to that sample, so that we can better estimate nutrient levels as well as fertilizer recommendations. So in this situation, sand and clay will have different densities, which will affect the final results based off of a fertilizer recommendation. Sand being more dense based off of the material, while clay finer particles will give you a much lower number when you apply that to fertilizer recommendations. Another application comes from either concrete or septic field specifications. And for both of these types of materials, septic fields and concrete, the material needs to fall within specific criteria. Otherwise, the material will not be suitable. When it comes to septic fields, if it's too coarse, the material will not retain any of the material coming into the septic field, so it could easily flow out into a water source, into the water table. If it's too fine, it might not act as a good dispersant, so the material may clog, causing tanks to back up. When we apply it to concrete, if the material is too coarse, the concrete will be crumbly and will come apart because there's not enough surface area to retain it. But if it's too fine, it's the opposite issue, where it will aggregate together and may crumble or be washed away because of the aggregates formed. In both of these situations, we apply ASTM C33 specifications, which can be shown easily on a particle size grain size curve, where we have the green Goldilocks zone, we can call it, where if the particles fall within that zone, it will be suitable for those types of applications. In a situation where it falls to the left of the Goldilocks zone, the material could be too coarse. And if it falls on the right side of the Goldilocks zone, it would be too fine of a material and not usable in those types of applications. When we apply particle size analysis for roadways, it can really affect the soil that's underneath the roadway, can affect how well the road will hold up to certain environmental instances. So when we look at it. If the soil's too fine, Saskatchewan has very high clay soils, so it's very fine. They have their own special evaluations that need to be applied. And when we look at if you do not take the soil particle size in consideration when you put down roadways, it can lead to shifting, washout, or severe damages. So this is the example of a roadway that was severely damaged because of a washout and the road crumbled away. And the AASHTO regulations for highway construction define the limits. So looking at that, it's similar to the grain size curve where there's a special zone that's best applied. And I don't really have a good graph of that or good grain size curve showing that application. But this is a couple tables that show the types of particle size that are important for road classifications. If a soil or aggregate is going to be used for these applications and it wants to be excellent or good, we expect it to have the Sieve Analysis percent passing a number 40 Sieve being 50% or less, while the percent passing 200 Sieve or that 0.075 mm being maximum of a 25. So what that tells us is that if the soil meets those criteria, it's going to be excellent for applying to this type of grade, while if it's not within that, if it's less than 36, for example, or very fine material, then it can be a fair to poor material, which is not going to be as suitable. So applying these types of regulations is very important, and knowing your classification systems is important. So moving on to where you can get this type of testing done. In Canada, there's a number of labs that offer grain size determinations. Our Saskatoon, Waterloo, and Winnipeg labs all offer grain size determinations. And a number of labs in the Prairie region, including Calgary, Edmonton, Saskatoon, and Winnipeg, offer the sand silt clay determinations. All of our labs have our CCME regulation analysis, so that's that particle size based off the 0.075 mm. In the United States, we do have our Tucson and Kelso labs that can do grain size determinations as well, following the ASTM 422 and their successor methods. So at this point, I would like to thank everyone for attending and open the floor for any questions.
Thank you, Dwayne. Yes, we will go ahead and open it for questions. Just as a reminder, feel free to use your chat box, your ask a question box, or you can even use your raise your hand to ask Dwayne a question. And we'll go ahead and give everyone a few moments. It looks like we do have one person's hand raised. Carl, I will go ahead and unmute you if you wanted to ask your question. Go ahead, Carl.
I'm just wondering, have you ever heard of anyone using particle size analysis to estimate the hydraulic conductivity?
I have heard of certain engineering firms that do use the particle size analysis in the hydraulic conductivity estimations, yes. A lot of those types of applications are done by geotechnical engineers, and yeah, I do know that there are people that use that for that application, yes.
Okay, cool, thanks.
As we give everyone a few more moments, again, to either use your ask a question box or the chat box or raise your hand. I do want to let everyone know that this webinar presentation has been recorded. All of the participants on this webinar today will receive a follow-up email once the recording is available to view. We post our webinars on our ALS Global website and on our YouTube channel. There we also post and you can find a wide range of video resources and past webinar Wednesday presentations. All right, it does not look like there are any additional questions at this time. I want to go ahead and thank everyone for attending today. Thank you again, Dwayne, for the presentation, and everyone enjoy the rest of your week.